Hey guys, welcome back. Day 42. We're calculating enthalpy today. And we're going to start off with one of the things we just fits in right now is the Born hypercycle, which is ionic bonding. Like the energy transfer the overall picture when an ionic bond forms. Okay? Why does it happen? There are 5 steps. All right? And so if we write out the equation, I have Na solid plus 1/2 of chlorine gas, right, because I only need 1 Cl, going to sodium chloride solid, all right? If we were to do this reaction, which I do not recommend doing at home, please don't do this reaction at home, right? Sodium is a metal, very reactive, explodes with water. Chlorine's a poisonous gas. We don't want you guys playing with those, all right? We don't play with those in the lab. However, if you're doing it at home, you'd see a greenish yellow gas go around this metal. You'd see a flame, and you'd see sodium chloride form. It's really fast. But we're going to break it down into different steps. All right? And so for the electron here on sodium to go to chlorine, as we have in our product here, right, to make sodium chloride, there are some steps. And we have some definitions. Right, so removing the electron from sodium, right, we actually have a term for that. We have a process for that, and ionization energy is that process. And ionization energy is the energy required to remove an electron from an isolated atom or ion in the gas phase. Right now we are solid, right? We are solid. So the first thing that we have to do, all right, is go to Na gas, and that's called sublimation. All right, and so as you can see on the bottom of the screen, right, that is positive 108 kilojoules per mole. That's the amount of energy required to make sodium a gas. And then sodium is going to become sodium metal, ion, sodium gas, that's an ion, right? We're going to lose the electron, and that's ionization energy. And that happens to be, if we look down, I have it down here, ionization energy, there's only one for one electron, it's 496 kilojoules per mole. And so now we have the energy required to get that electron off of sodium. Now we got to talk about chlorine. Chlorine comes as, right, Cl bonded to Cl. We technically have to break that bond, don't we? We have to break that bond. And so step 1, that's a little long, but that's okay. Step 1, right, would be breaking the bond. And that energy, like the bond energy, we have 122. So technically, it's 1/2 of 243 kilojoules per mole. And to 3 sig figs, it's 122. Right? And then we get Cl. Gas, it's already a gas, and then we have a step on going to Cl minus gas. I don't know if you remember that, but that would be electron affinity, right? The electron affinity, and the electron affinity is negative 349. All right, remember electron affinity was the energy associated with the addition of an electron to an isolated atom or ion in the gas phase. All right. And then when we add these up, and then they go to sodium chloride, step 5 is our lattice energy. All right. And that is the energy change, right, associated with, right, the formation of a crystalline lattice of alternating cations and anions from the gaseous ions. That's lattice energy. All right. Okay, that's what it is. And so if I were to look at it, this overall energy change here, right, which we are going to call the overall energy change, is right here, delta HF, this enthalpy of formation. All right, so we got delta HF of NaCl. That would be equal all our steps. So step 1, all right, was sublimation, which was positive 108 kilojoules per mole. Now I have step 2 being the bond breaking in my list here, so we can call that step 2, right? Bond break. Break the bond of, or bond dissociation, which is 122. Step 3 was my ionization energy, which was 496. Step 4 looks like it's going to be our electron affinity, which was negative energy released, negative 349. And step 5 is our lattice energy. In this case, it's negative 787. And so overall, we got negative 411. So all those steps happen, right? How do we calculate? Now this is how humans calculate it, all right? And then, again, it's a very good predictor, so it's really good to do, but that's what we have for our lattice energy and our boron hybrid cycle, and why some of these things form, so some of these don't form. All right. Oh, I already have the lattice energy definition right here. Right here. Right there's your lattice energy. Now, size and charge, size of the ion and charge of the ion are important. Okay. And why? Okay. And so as the size increase, well, let's look at this. So we have the size. Typically, cation, it didn't drop to a circle. Cations are positive and anions are negative, right? And anions are usually, that's not a circle, I want a circle. Anions are usually much bigger, right, than this. And now sometimes, as you learn, sometimes they touch, sometimes they don't touch. Sometimes there's space. All right? Okay? Size and charge. And so there's going to be a distance between them. All right? All right? R. There's a distance between them. However far apart they are. All right? And you look at Coulomb's law. Right? The energy is equal to 1 over 4 pi permeability free space. Those are constants. Times, we got the cation charge, Q1. The anion charge, Q2. All right. Divided by, oh, that's a multiplication. Divided by R. Okay, so what happens? As R, look at R. As the denominator gets bigger, E gets smaller. So as they get closer together, as R is getting smaller, E gets bigger, right? And so there's our size, right? There's our size, okay? As we have a smaller radii, bigger lattice energy. Bigger radii, smaller or less energy is released when they form. And then the charges. As the numerator gets bigger, E gets bigger, right? So they're more negative with more charges. So this means like small ions, like lithium and sodium, actually even magnesium, right? Small positive, aluminum, small and positive, right? And then small negative ones like oxide, nitrides, right? Those are going to have largest lattice energies. And if you look at like cesium and iodide, bigger ions, smaller charges, less energy release when they form. So that's the boron hybrid cycle. All right, and now all we're going to do now is more calculations. Let's do an example. All right, and so using the data provided, calculate lattice energy of calcium chloride. Kind of fun. What do we have? So now calcium chloride has, let's write a reaction first, and then we'll go there. So we're making calcium chloride. Ca solid plus Cl2 gas goes to CaCl2 solid. All right, so ionization energies. First ionization energy of calcium is 590. The second ionization energy for calcium is 1145. Electron affinity for chlorine is that. Delta H is that. Sublimation, right? You have these two to use. And then we have the bonds here for Cl. And we got calculate the lattice energy of calcium chloride is our situation. All right, so now we know that calcium has to sublime, right? Step one was sublimation. We'll just do that, sublimation. And we're going to go to Ca gas. And how do I do that? I'm going to use these delta H's. 179.3 kilojoules per mole minus 0. All right, because we're going to do the product minus the reactant. And then what else do we have? We have, once we're at calcium, let's just go ahead and do our ionization energies. We got, we'll call this one 2, IE1, which is 590 kilojoules per mole. And that gets us to calcium plus gas. And then we have IE2, which is 1145 kilojoules per mole, which gives us calcium 2 plus gas. Step 3, we'll do the bond breaking. And so we'll go to 2Cl gas, right? And what is that? So in green here, Cl, I have 2 times 121.7 kilojoules per mole minus 0. So that's 242 kilojoules per mole. And so now we have two Cl gases, what's the next step? So it's 244. I can do math. And so then we got 4 was our electron affinity. And that's going to go to 2 Cl minus gas. And since the electron affinity is negative 349 kilojoules per mole, there are 2 of them, so we have to double that. And so negative 349 times 2 would be negative 698 kilojoules per mole. And then finally, step 5 will be our lattice energy. All right, so now let's do the math. Delta H, F for CaCl2. It's going to equal 1, 2, 3, 4, and 5. So step 1, sublimation. Step 2, the ionization energies. Step 3, the bond breaking. Step 4, the electron affinities. And step 5, lattice energy. And I'll write all that out. So we have the enthalpy of formation. We have sublimation. Of calcium. We have ionization energies. One and two, first and second. We got bond dissociation or breaking. We got electron affinities. And then we have lattice energy. Now, with this, we are looking for lattice energy. All right. And so I'm just going to leave it this way. You could move everything to the other side. 1, 2, 3, and 4 on the other side, and which we'll do. All right. We can do that. And so if we look at our math, we have, it's negative 75.8, right? Yeah. Negative 795.8 kilojoules per mole. And we're going to subtract sublimation. Well, let's just do it this way. Sublimation was 179.3. Kilojoules per mole. Plus, we have IEs 1 and 2. 590 kilojoules per mole. Plus 1145 kilojoules per mole. Plus the bond breaking, that was 244. Plus the electronic affinity, which was negative 698. Plus our lattice energy. That's what we're looking for. All right, so now we just subtract, move everything over. So I got negative 795, so negative 795.8, subtracting 179.3 minus 590 minus 1145 minus 244 plus 698. And I get lattice energy equal to negative 2255.8. And I really only have, I don't know how many sig fig, I don't know how, 592 really. So negative 2,300 kilojoules per mole. That 590 might be 3 sig figs. If that's the case, then it's negative 2260 kilojoules per mole. If 590 is 3 sig figs, which the problem doesn't tell you, so you're assuming, so negative 2300 kilojoules per mole it is. And that's how we would do that. Now that's a long, long problem. So I normally don't test people on that because of how long it is, which most of my students are relieved. But that's what the Born-Haber cycle is. All right, coming up next, more enthalpy calculations. How much heat is liberated or released? Highlighted. How much heat is liberated in the combustion of 206 grams of hydrogen? Now it gives you the heat of combustion, all right? And what's important about this is for 1 mole H2, okay? So combustion of hydrogen, H2 gas, plus O2 gas, going to H2O liquid, because we're in chemistry land. All right, now it'd be a 1/2 here. So now, because we want to have a 1 here. So we'll do the 1/2 and 1. We'll make that work out. So now we have 206 grams of H2. All right, well, what has to go on the bottom? Grams of H2. 2.02 grams of H2 is 1 mole of H2. And we're going for heat, right? We're going for heat. And so we know that 1 mole of H2 produces negative 286 kilojoules of heat. All right? And so if I do the 206 divided by the 2.02 times the negative 286, I get negative 29,200 kilojoules. So that's how much heat is released when 206 grams of hydrogen is burned. All right. Next one. Okay. Propane. Now, to be honest, I stole this problem again from Michigan State. I love this problem. I think it was one of the homework problems, but I really like this problem. All right. I'm from up north where it's cold, and so heating a pool is somewhat important for a lot of people, right? Because that small window of summer, you can use it a little bit more, right? And so I love this problem. This is one of my top 5 favorite problems, and again, I'm not sure who wrote it, but I got it when I was a grad student at Michigan State. And so I really like this problem. Now, there's 2 problems with this. The first one's not my top 5. The second one is, all right, the swimming pool. But let's dive into this. So propane is used to produce heat by burning, and we have a balanced chemical equation, right? There's technically a 1 here, a 5, a 3, and a 4. And the standard enthalpy of formation is that. How many grams of oxygen will we need to produce 500 kilojoules of heat? Well, that's 4 sig figs, so let's start. I have 500.0 kilojoules of heat. What's my ratio? Well, kilojoules has to go on the bottom. And because I have kilojoules on the bottom, I know it's going to be negative 2,044 kilojoules would be 5 moles of O2. Right? Because we have the delta H for the reaction overall. So every time this one process runs, I get negative 2,044 kilojoules. So I need 5 moles of O2 to make 2,044 kilojoules. And then, we're in moles of O2. We better go to grams. We want grams. So we know 1 mole of oxygen gas is 32 grams of O2. And if we do this, I get I have 4 sig figs, right? So I have 500, times 5 times 32 divided by negative 2044. I get 39.14. 39.14 grams O2. And now, in class, I would always ask students, hey, does that sound good? And I get a lot of yeses. And my question is, can we have a negative mass? Because if we can, that'd be great, wouldn't it? Here's negative 10 pounds for you. Here's negative 15 pounds for you. Right? That'd be awesome. All right? You would be very wealthy in this country if you could sell negative weight to people. It doesn't exist, does it? Right? It doesn't exist. Mass is always positive. So what does this mean? Down here, this means that it's exothermic. It's very similar to money, right? Money is always positive, but you can owe somebody $20 or somebody could be giving you $20, right? And so if I owe somebody $20, if $20 leaves me, it's negative to me. If $20 comes to me, it's positive, right? Same thing with energy. So when this process is going on with propane, energy is leaving the propane and oxygen, right? And that's fine. So 30, that's what's going on. The energy is leaving. Doesn't mean the energy is negative. It just means it's leaving the system. So it's going to be a positive mass. That's very important. That's like a direction, not a value, if that makes sense. All right, next one. This is the big one. This is the top 5 right here. Swimming pool, 20 meters long, 2 meters deep, and 5 meters wide, filled with water. The temperature of the water is 22 degrees Celsius. The other pool would like the temperature to be 32, which is like bath water. Here's your question. How many grams of propane would have to be consumed if all the heat from the combustion went to be absorbed by the water? Which doesn't really work, but that's what we're going to do it. All right, so we have a pool. It's 20 meters, 2 meters, and 5 meters. All right, we're at 22, but we would like to be at 32. All right, so let's see here. If I have a pool, that's an arrow. Let's try a rectangle. Not snapping for me. There we go. Down a little bit. Maybe I put the pool in. It's a little off. All right. We have 20 meters, 2 meters, and 5 meters. So the volume of the pool would be 20 meters by 2 meters by 5 meters. So that would be 200 meters cubed. That's great. What are we physically doing to this water? All right? What are we doing? We're trying to put some propane underneath there, some 33H8, and we're trying to burn it, right? Like a little flame there, little flames coming up, right? We're burning that, right? So I need to change the temperature of the water. How do I change the temperature? What formula am I going to use is the question, all right? Or do I have a formula that we just learned about that has heat to temperature change? I think we do. I think heat Q equals the mass of the water, specific heat of the water, times the delta T of the water, right? So I know I got to figure out Q. I need to know how much heat we need to have. Mass of the water. I need the mass of the water. I have the volume of the water. C is a constant. Specific heat of the water, we got that. It's 4.184. That's a constant, right? All right, delta T, right? It's 32 degrees Celsius minus 22 degrees Celsius, right? It's 10 degrees Celsius. We got that. That's easy. Mass, we have to calculate. How are we going to do that? We know we have 200 meters cubed of water. And we know the density of water, right, H2O, the density is 1.0 grams per milliliter, right, or gram per centimeters cubed. All right, so we need to do some conversions here. So we know 200 meters cubed, excuse me, I forgot the 3. There we go. So we know, hopefully, we can use your sheet so you don't have to memorize this, that for every 1 cubic meter, there is 1,000 liters. So 1,000 liters per cubic meter. I don't know if you remember that from before, but there you go. And then for every 1 liter, there is 1,000 milliliters of water. And for every 1 milliliter of water, there is 1 gram of water. All right? And so our mass of the water would be 2 times 10 to the what? 1, 2, 3, 4, 5, 6, 7, 8. 8 grams H2O. That's a lot of grams. Right? That's 200 million grams. Right? Swimming pools are pretty heavy. I mean, this is a big pool, right? 20 meters is a long, like you can do laps in this pool. All right? So now we can figure out heat. The Q, the energy, Q, well, let's use red. Q, the heat, is equal to the mass of the water, specific heat of the water, delta T of the water. All right? And so Q would be equal to the mass, 2 times 10 to the 8th grams. Our specific heat of 4.184 joules per gram degrees Celsius. And it was 10 degrees Celsius is what we used, right? 10 degrees Celsius. That was the 32 degrees Celsius minus 22 degrees Celsius. So Q, the amount of heat we need, is basically 8. We'll use an extra sig fig, so 8.4 times 10 to the 9th, it looks like. 8.4 times 10 to the 9th joules. All right. So if I take my 8.4 times 10 to the 9th joules, and let's convert that to grams of propane. So I know how much propane I can figure out how much propane I need because I know how much energy I need, right? And so we're going to convert. And remember, it's exothermic, so it's negative 2,000. Well, no, we can't do that yet. I need to know that there are 1,000 joules of heat and 1 kilojoule of heat. All right, I gotta go to kilojoules. Why? Because this is negative 2,044. Kilojoules is 1 mole of C3H8. And then we can go 1 mole of C3H8, 12.01 times 3, plus 1.01 times 8, right? Those are our molar masses. I get 44.11. Right, and remember, this just means exothermic. And so overall, I get 1.8 times 10 to the 5th grams of propane, which is about 180 kilograms, which is a lot. That's a lot of propane. But that's it. So I like that one because you have to do 2 concepts in one, right? And it's an actual problem that people actually do. Some people actually do heat their pool with propane. All right. I don't have a pool, but I would love a pool. But that's what we got. So there's the propane. There's the pool problem. Next one. Consider the following reaction. We got C2H4 plus F2 going to C2H4F2. Gives you delta H for the reaction. We are trying to estimate the carbon-fluorine bond energy. And it gives you the other bonds. All right? So we have a CC bond. We have a C double bond C bond. We'll do this color. And we have FF is that one. All right, so this is the bond energies, right? And so for bond energies, if you think about it, remember, delta H can be approximated to the energy of bonds broken minus the energy of bonds formed. So bonds broken minus bonds formed. So we got to figure out what's going on here. So C2H4, valence electrons. Yep, there he came back. All right, so for carbon, I have 4 valence electrons, and there's 2 of them. So 2 times 4 electrons plus 4 times 1 electron. So that would be 8 and 12 electrons, right? And then F2, 2 times 7 electrons would be 14 electrons. All right. And then we'd have 26 electrons here because we're just adding them together. All right, so C2H4, I'm thinking carbons are in the middle. H, 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 H. All right, so let's see here. We use this here. 2, 4, 6, 8, 10, 12. I think that's good. F2, F to F. 2, 4, 6, 8, 10, 12, 14. All right, on the other side, what do you think it looks like? I'm guessing, if I had to guess, that an F would go to each C, kind of, right? I would assume that we would break apart this double bond, right? Just use a single bond there and then put an F on each side. So let's try that. F, C, C, F, H, 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 H. All right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I think that looks great. All right, what bonds are broken? Well, if you look, first of all, what bonds don't change? If you look, the C to the H's, these are on both sides, right? I don't think those are involved. I just think the broken ones, right, the broken bonds would be here and here, and the formed bonds would be there, right through the middle. I think the CHs don't change, which is nice because we didn't get the CH bond energy, so that's kind of a good hit. So delta H would equal bonds broken, which would be let's do C double bond C and F single bond F. So the bonds broken minus bonds formed, which we have C single bond C and 2 C F. All right, let's plug in some numbers and solve. So delta H is negative 549 kilojoules per mole. It should be kilojoules per mole. The C double bond C, I use that here, is 614 kilojoules per mole. Plus FF, which is 154 kilojoules per mole. minus the C single bond C, I use green for that, 347 kilojoules per mole, minus 2 times the CF bond. Excellent. Now it's algebra time. All right, so negative 549 kilojoules per mole equals, I think if I do 614, 154, I think I get 768 kilojoules per mole minus 347 kilojoules per mole plus 2 times CF. So very important, right? This negative 1 is distributed to both, right? Both. Oh, but the problem is I messed up, didn't I? Hopefully you caught me. Hopefully you caught me. This should be a plus there. And so now this becomes a minus because it is distributed to both. All right. And so if I take both of these numbers, the 768, add them together and move them over, I get negative 970 kilojoules per mole equals negative 2 times CF. And so that means I think the CF bond would be 485. All right, so I want to point that out. I did it right here. That's where most of the mistakes. I just did it too, right? Where this, I made a mistake translating down the positive down. I made it the wrong sign, and then I distributed the wrong, right, incorrectly. Some people don't distribute, right? That's where a lot of mistakes of this is, because once you get to this part, right, that's algebra, right? But a lot of times the mistake is in right there, right? Moving on. So I'm glad that happened. So that's a pitfall. Watch out for that, and just take your time. Take your time. All right. Let's see. Ooh, we have another one of these. All right. Balance equation for the reaction of methane with oxygen gas forming carbon dioxide and water. So we got to write a balanced equation. Methane, CH4 gas, oxygen gas, O2 gas, going to CO2 gas and H2O. It doesn't say, so we'll put an L down because we're at 25 degrees Celsius. Obviously, methane probably makes gaseous water when it burns, but we'll go with it. All right, 1 carbon, 1 carbon. 4 hydrogen, 2 hydrogen. I need to put a 2 for H2O. All right, so then that gives me 4 oxygen on the right side. I think a 2 here is good. I think that's all it is to balance. Hopefully, we're pretty confident with balancing reactions. All right, so this is a bonds broken and a bonds formed. It tells you that, basically. List the bonds broken and the bonds formed. All right, so Lewis structures. Carbon, 4 electrons. Plus 4 times 1 electron, right? 8. 2 times 6. 12. 4 plus 2 times 6. So that would be 16. And then 2 times 1 electron plus 6 electrons, 8 electrons, right? Highly encourage you to do that each time. So beginning, we got carbon in the middle, 1, 2, 3, 4 H's, 2, 4, 6, 8. I think that's good. O2, OO. Hopefully you guys remember it's this. All right, O2, CO2. Again, hope we remember that one too. Purple here. 2, 4, 6, 8, 10, 12, 14, 16. And water. All right, so now we got bonds broken and bonds formed. All right, and all the bonds are broken and all the bonds are formed. So delta H of our reaction is equal to bonds broken minus bonds formed. All right, so delta H here. Bonds broken. I have CH, we'll just write CH and O double bond O, right? Now, how many of each? That's the question. I have 4 CH bonds, and I have two O2s, right? You guys see that? Two O2s, right? I only have one methane, but I have two oxygens, so I need two O2s breaking. Bonds formed. I have C double bond O and O double single bond H. Question is how many of each? I would have two CO bonds, and then I would have 1, 2, but there's two, so I have 4 OH bonds. All right, now let's put in some numbers. 4 times CH. CH is 413. Plus 2 times O2 is 498. Minus 2 times CO was 732. And 4 times OH, which was 463. All right. So now, you can do that math. If you need to break it up, the bond's broken, get a number. Bonds formed, get a number. And then add them, you can. Feel free to do that. Delta H, the reaction, is equal to, I got negative 668 kilojoules per mole. All right. Go ahead and pause. Make sure you can do it. Right? Always feel free to work ahead in these videos, right? But pause, make sure you can do it. And then double check. Now, the question wasn't just what delta H is. It says to calculate that, right? Then, all right, calculate the energy released. So that's what we got to do. We got to calculate the energy released when 78.2 grams of methane is burned. So now we have 78.2 grams of CH4, and I want to heat. I want how much energy is coming out. So I got grams of methane. What do I got to go to? I got to go to moles. Carbon's 12 plus 1.01 times 4. So that's 12.0. I think that's what we'll do. 16.05 grams CH4 is 1 mole CH4. All right. Now we know that 1 mole CH4 is negative 668 kilojoules. And so we take 78.2 divided by 1605 times 668. It's negative because it's exothermic, right? And that's negative 3,250 kilojoules. That's what I got. Hopefully that helps. All right. This next one. So now we have an example of reactions. So I have 2 reactions and I have to calculate a 3rd reaction. Hopefully we recognize this is Hess's law, right? You're the elimination, basically. And this was actual test question I gave one time, and it was supposed to be a nice one. So if I highlight, I like to do this. I like to make my reactants and my products. So I got SnCO4 liquid there as a product, and my reactants, SN, and the CLs. And if we look, right, if I add these, oh, that's a highlighter. I don't want to highlight. If we add them, this will cancel on both sides. And I would actually just, all I have to do is just add these up. Boom. If I add them up, I get the reaction. I didn't have to do anything to it. So I have to do negative, I just delta H, add them up. Negative 325 kilojoules plus negative 186 kilojoules. I think that's negative 511 kilojoules. That was all that one was. It was supposed to be a very nice, easy one. So I recommend colors. If you don't have colors, squares and circles, something, so you can recognize what side of the arrow they're on. But that's Hess's law. And that was an easier one of Hess's law. All right. Acetylene. Now this one's different. Now you're given delta HF. So acetylene reacts with oxygen gas to form carbon dioxide and water. Write the balanced equation. Okay. C2H2. C2H2 gas plus O2 gas goes to CO2 gas and H2O liquid fit, 25 degrees Celsius. All right, plus some heat. All right, so carbons not balanced. Need to put a 2. All right, hydrogen's balanced, but then I have an odd number of oxygens on the right hand side, so I'm going to have to, if I were to do this, I'd have 2, 4, I have 5, right? 2 times 2 is 4, 5 oxygens, so 5 halves. So I need to put a 2 there. I need to make that a 4, make that a 2. Does that work? I have 4 carbon, check. 4 hydrogen, check. 10 oxygens. 4 times 2 is 8, plus 2, 10 oxygens. Great. Now, the question in the problem, so we are at the balanced equation. Give me the following enthalpies of formation. How much energy is released when 3 moles of acetylene are burned? So we're starting with 3.0 moles. And I want to know how much heat. Because plus heat is over here. Plus heat. And how much? Not how many grams, but how much. All right, so when we have this, the standard enthalpies of the reaction is equal to the sum of the enthalpies of formation of products minus the sum of the standard enthalpy of formation of the reactants. All right, so delta H, we don't know. Products, CO2 and H2O, and we have 4 and 2. Reactants, C2H2 and O2, and we have 2 and we have 5. Now, if you notice, O2 is not listed. Why is O2 not listed? Right? Because it's an element in your standard state. So we don't worry about that because it's 0. Right? That's going to go to 0. Okay. So delta H of the reaction, 4 times CO2 is negative 394. Plus 2 times water, negative 286. And then minus 2 times acetylene is 227 positive. And 0 for O2. So delta H for me, if I do this, I do 4 times negative 394 plus 2 times negative 286 minus 2 times 227, right? I get negative 2602 kilojoules per mole of the reaction. So then we're going to take our 3.00 moles of C2H2. All right, and we know that there are 2 moles of C2H2 for every negative 2602 kilojoules of heat. And so it looks like we get, I got negative 3903, so negative 3900 kilojoules, which if I have 3 sig figs, which I think I do, I would need to put negative 3.90 times 10 to the third kilojoules to make that very clean. All right. So that's how you do the products minus the reactants. Now, there is one more. I'd recommend you pause and do it, and then come back. All right? I'd pause, do it, and come back. All right, hopefully you paused, did it, and came back. So we got a rate of balanced equation for ethanol. Now I'm gonna, this is kind of mean, this problem. I'm gonna write ethanol C2H5OH, kind of like it is here, C2H5, right? So we got C2H5OH plus PCl3, phosphorus trichloride, going to C2H5Cl plus H3PO3. All right. Oh, man. This is almost considered a double replacement reaction. So let's look. 2 carb. So if I'm going to keep that and that as 1. Does that make sense? Hopefully that makes sense. So right now there's one of those and one of those. 1P and 1P. Cl. Cl is an obvious. I need to put a 3 in front of this, which means I need to put a 3 in front of the ethanol. So now, let's look. I have 6 carbon, 6 carbon. I have 5, 6 times 18 hydrogen, 15, 16, 17, 18 hydrogen, 3 oxygen, 3 oxygen, 1 phosphorus, 1 phosphorus, 3 chlorine, 3 chlorine. We're good. Now, excuse me, we have 39.2 grams of ethanol is burned. Calculate, right? So we're going to calculate how much heat when that happens. Right? Calculate the standard enthalpy change and calculate the heat of the reaction. All right. So delta H, we got the delta HF, so delta H of the reaction is equal to the sum of the products minus the sum of the reactants. So delta, that's a horrible triangle. Delta H, standard of the reaction. Products, C2H5Cl and H3PO3. And there happen to be 3 of the ethyl chlorides minus the reactants, C2H5OH and PCl3. There happen to be 3 ethanols. All right, let's plug in some numbers, shall we? So delta H, we get 3 times ethyl chloride, which is negative 105 kilojoules per mole, plus H3PO3 is negative 972 kilojoules per mole, minus 3 times ethanol, looks like it's negative 277. And phosphorus trichloride would be negative 287. All right, so if we do 3 times negative 105 plus negative 927 minus 3 times negative 277 minus negative 287, Oh, because you hopefully already did this. I got delta H. Man, the reaction is equal to negative 169 kilojoules per mole. All right. So now we can take our 39.2 grams. Now, if you want to write it CH2OH or C2H3O2, either way works. All right. Times, we know that 1 mole of CH3CH2OH. I got 2 carbons, right? And so, right, remember the molar mass? 2 carbons at 12.01 plus 3, 4, 5, 6 hydrogens at 1.01 plus 1 oxygen at 16.00. All right, that's everything. That'd be, what, 4608. And then here's our delta H right here. We have 3 moles of ethanol is negative 169 kilojoules. So if we take our 39.2 times our negative 169 divided by 4608 divided by 3, I got 47.9 kilojoules. All right, that concludes the video. That concludes everything for this chapter 2 on energy in Chem 1. So if you have any questions, feel free to reach out. Otherwise, we'll see you next time. Take care, guys. Goodbye.